morning, students. Welcome to this video. In this video, I will try to teach you something about circles of grade 10. You have already studied circles in grade 9th. And as for grade 10th is concerned, there are two topics related to circles. One is areas related to circles, and one is circles. Now, in this topic on circles, we'll try to understand what we mean by tangent to a circle. So we'll be defining the term tangent. So let me write the lesson objective to define tangent. To define the term tangent. To define the term tangent. And we'll try to study its properties. Study its properties. So let me try my best to explain the term tangent and what are its different properties as far as circle is concerned. You haven't heard of word tangent in grade 9. This is a new term for you. Let's try to see what we mean by the term tangent, and after that we'll try to study its properties. Now, if you draw two curves, those two curves could be homogeneous, they could be heterogeneous. Let me draw two circles. Now, these two circles, they are intersecting at 2 points. Again, these two circles, they don't intersect at a point. And one other situation, these two circles, they intersect at 1 point. So, these two circles, they don't intersect at a point. These two circles intersect at 2 points. These two circles intersect at 1 point. Now, when two circles intersect at 1 point, not necessarily circles, they could be other curves. Curves could be homogeneous, they could be heterogeneous. When two circles intersect at a point, we say, like this is circle A, this is circle B. I would say circle A and circle B are tangent at point P. So the word intersect has a better name as tangent. Circle A and circle B are tangent at point P. Now here also circle A and circle B are tangent at point P. Now what's the difference? Here they intersect internally and they intersect externally as for this case is concerned. So the word tangent means when two curves intersect at a point. Right? Now, as far as this topic is concerned, we'll be having two different curves. See, these are two homogeneous curves. We'll be having two heterogeneous curves. And we have to see how this tangent is all about. If I draw a circle and I take a line, this straight line is AB and this is circle, call it C or C1. Now this circle and this straight line, they meet at 1 point. This point is P. So I would say that this circle is tangent to the straight line AB, or AB is tangent to the circle C1. Both are correct. But these two curves are heterogeneous. And they are in the same plane. They are coplanar. Now this line AB, as we say it's tangent at the point P, we also say that the line AB is tangent. It's tangent at point P, and line AB is also known as tangent, or we could say this is known as line of tangent C. The point at which it meets the circle is known as point of contact, or it's also known as point of tangent C. Now, what are the properties as for this tangent is concerned? We have two theorems as per your syllabus is concerned. They are based on the properties of a tangent. The first theorem says that if there is a tangent at a point P, you have to prove that the radius that is being drawn through the point of contact, it will be perpendicular to the tangent. As per your NCERT textbook is concerned, this being the first theorem, prove that the tangent is perpendicular to the circle through the point of contact. So this is one of the properties. Let's try to prove this result. Okay, so what's given? See, you are supposed to write, usually you get a 3 mark sum as far as circles is concerned. You are supposed to write given to prove construction and all details so that you don't leave any room for the examiner to deduct marks. So given is a circle with center C. A circle with center O and a tangent. What is that tangent? That is AB at point P. And we know OP is the radius. Okay, this is given. Now what we have to prove? we are supposed to prove that this radius and this tangent, they meet at 90 at P. That means in simpler terms, I have to prove that OP is perpendicular to AB. Now, we need some construction. What construction will do? Let's see. See, as for AB line is concerned, there are infinite points on AB. Let me take any point on AB, on tangent AB. Let me take a point, suppose Q. Now, this point is on the tangent and it's outside the circle, right? So what I will do, I will join O with Q. So construction would be take a point Q on AB and join OQ. Now, let's see how we are going to prove it. Now, if you observe, we could say, see, OQ is intersecting the circle. Let's name that point, for example, at T. Take a point Q on AB, join OQ, we could say intersecting the circle at T. See, if you observe OQ length, which is a line segment, is OT plus TQ. OQ line segment is OT plus TQ. But OT is equal to OP. You could observe it. OT and OP are the radii. So I could replace OT by OP. Now let's observe. Let's see the relation between OP and OQ. OQ is OP plus TQ. So OP is a part of OQ. So whole is greater than the part as per Euclid. So this means that OQ length is greater than OP because OP is a portion of that. OQ is greater than OP, or in other terms, OP is less than OQ. So you are making a comparison between the line segment OP and OQ. We observe that OP, which happens to be the radius, it's smaller than OQ. Now, if you take different points on AB to the right of P or to the left of P, so many points could be taken. And when you apply the same logic, you observe that OP, which is the radius, is less than all those line segments that have been drawn from O to the line segment, to the straight line AB. What I do, see, this is my AB, which is a straight line. This is my O. This is OP, which I have to prove it's perpendicular. So we have compared OQ with OP. If you take different points, maybe OR, OS, and so on, and compare them with OP, we have the same conclusion, that OP is smaller than all those line segments that could be drawn from a point to the line. And if you recollect, there is a result in grade 9th, you studied that in grade 9th, that of all those line segments that could be drawn from a point to a line, of all those line segments that could be drawn, the perpendicular is the shortest. Since OP is shorter than all those line segments, so OP is the shortest. That means that OP is perpendicular. So that proves that, therefore, angle P is 90. Why it's 90? Because OP is the shortest line segment of all those line segments that could be drawn from O to AB. Hence, OP is perpendicular. So that proves this result. Now, how to remember? In fact, this is a theorem. You could remember this result as tangent radius theorem, because this result talks about the relationship between tangent and a radius in a circle. So do remember it as tangent radius theorem. So tangent radius theorem simply states that the tangent is perpendicular to the radius through the point of contact. Now, this was one of the properties of tangents to a circle. There's one more property, so I will take that property. That happens to be the second theorem. After that, we'll move on to the application part. We'll try to attempt sums as far as textual sums are concerned, applying these two theorems. So let me just rub it now. Now, the second theorem, it states that the tangents that could be drawn from an external point to a circle. But before going into that, let's see what are the different situations in which a tangent could be drawn to a circle, taking into consideration the points inside the circle, on the circle, and outside the circle. So if I draw a circle and I take a point P, this is inside, it can be center also. This is one situation. One more situation, again I have a circle and I have a point P on it. And third situation, I have a circle and I have a point outside the circle. I'm naming that point as P. These are three situations. Let's see how many tangents could be drawn. If I draw a line, straight line passing through P, so many lines could be drawn. As per Euclid, infinite lines pass through one point. Now, are these all lines, are they tangent to the circle? Let's try to observe. They are not tangent if you observe. They are not tangent because they intersect the circle at 2 points. Tangent intersects, rather it meets the circle at 1 point. They are not tangents, they are secants. Secant is a straight line intersecting circle at 2 points. What about this? A point on the circle. You can draw a tangent, but only one tangent. And what about this? From this, you can draw two tangents. In fact, as far as your construction is concerned, there's a construction how two tangents could be drawn from an external point to a circle. Now, these are three situations as regards that if there's a point in the interior on the circle, outside the circle, how many tangents could be drawn? Here, none of the tangents could be drawn. In this case, one tangent is drawn. In this case, two tangents are drawn. And as far as our second theorem is concerned, it's all concerned about this, that from an external point, if two tangents are drawn, prove that they are equal in length. Prove that they are equal in length. Now a question arises. Just now I said tangent is a straight line. Now if these are tangents, how come you are finding their lengths? But do observe that these tangents, they meet the circle at 2 points. So this PA and PB, they are tangents as well as they are segments because it has two endpoints. So they are tangents from external point. We call them as tangent segments because they have two endpoints. So we have to prove that these two tangents drawn from the external point, they are equal in length. So what should we write in given? So given would be, let me write here, given a circle with center C. See, usually we write with circle CO, R. This is symbolic writing. This means it has center O and the radius is R. A circle with center C, radius R, with two tangents PA and PB drawn from external point P. Now what you have to prove, my dear friends, do observe, we are supposed to prove that the length PA, this tangent segment, is equal to length PB. Okay, what construction we will do? We'll join OA, OB and OP. So join O with A, O with B, O with P. So why we do this? We do this so that you get two triangles in the figure. Now you have two triangles in the figure. So you have to prove that this line PA of one triangle is equal to the length PB of other triangle. So what we are going to do, we will be making use of congruence. If you make these two triangles, this triangle congruent with this triangle, then PA will be equal to PB as per CPCT. So let's try to make the triangles congruent. So proof would be, say in triangle POA and triangle POB. So how you observe? I have to show PA equal to PB. Do observe this angle is 90, this is also 90. Angle A is equal to angle B, each 90 degrees, as per tangent radius theorem. And OA is equal to OB, right? OA is equal to OB, the radii of the same circle. Radii of the same circle. And OP is equal to OP, that is common. So these two triangles are congruent by RHS. right hypotenuse side. So when these two triangles are congruent, I repeat, angle A equal to angle B, each 90, OA equal to OB, radius of the same circle, PO equal to PO, common in both, so triangles are congruent by RHS. When triangles are congruent, so PA equal to PB, that is CPCT. So that makes these two tangents from the external point, they are equal as far as this circle is concerned. So how we remember, how we retain this theorem? We retain this theorem as tangent segment theorem. So two theorems we have discussed. One is tangent radius theorem and one is tangent segment theorem. And now what we'll do, we'll apply these properties of these tangents as far as circle is concerned to the geometrical problems. So I'll be taking problems from the textbook. If time permits, we'll take sums outside the textbook. Okay. Now, first question. So my next lesson objective is to apply the knowledge that we have learned to the geometrical problems. This is the second lesson objective. Okay, let me take a question regarding this. It says that from a point P 10 centimeters away from the center of a circle. So there's a circle, let's draw the circle. There's a circle. Okay. There's a point 10 centimeters. From a point 10 centimeters away from the center of a circle, a tangent PT of length 8 centimeters is drawn. So this is point P, this is away from the center, and from this point a tangent is being drawn. PT is tangent, so this would be radius. Now what's the length of the tangent? Length of tangent is given to be 8 centimeters, and this is 10 centimeters. This distance is 10 centimeters, this distance is 8 centimeters. What we are asked to find the radius of the circle, that is R. A question worth 2 marks. So in this diagram, you simply have a right angle triangle. Now P is an external point whose distance from the center is given, and from PT a tangent has been drawn. You joined O with T, you have radius. So what do you have? You have a right angle triangle, my dear friends. It's simply a right angle triangle. In this right angle triangle, 2 sides are given and you are asked to find the third side. This is a situation that you have already dealt in grade 7th and 8th. It's a case of Pythagoras theorem. So we'll apply Pythagorean theorem in right angle triangle because angle T is 90. So simply you would say in right angle triangle, OTP. Apply Pythagorean theorem or Pythagoras theorem, whatever you want to call it. Apply Pythagorean theorem. So it says that PT square is OP square plus OT square. Now PT is 8, square of that. No, it should be OP square. There's a correction, my dear friends. Hypotenuse is OP. OP square is PT square plus OT square. Hypotenuse is always the side that is opposite to 90 degrees. Now OP is 10, square of that. PT is 8, square of that. And OT is R, square of that. This is 100. This is 64 plus R square. 100 minus 64 is R square. 36 is R square. So you have to take the square root on both sides. Square root of 36 is R. So R is 6 centimeters. So the radius of the circle is 6 centimeters. So we have applied the tangent radius theorem to this very sum. You have number of sums being asked wherein the radius is given, hypotenuse is given. You have to find the length of the tangent. So all sums could be done. You can give a try. Now we'll move on to one more sum. So these are all textual sums. Okay, I will rub this. See, sometimes you get a question wherein you apply the tangent radius theorem. Sometimes you get a question in which you apply tangent segment, and you have some questions in the textbook in which you apply both the results, both the properties. So there's a question like this, that there are 2 concentric circles. So 2 two concentric circles are there. This is one circle. This is one more circle. Okay. Now for these two concentric circles, AB is a chord of the larger circle, touching the smaller circle. AB is a chord of the larger circle and it's tangent of the smaller circle. So I have to show that AC is equal to BC. This is question number 2. So given a circle C1 and one more circle C2 with common center O. So two circles, C1 and C2, two circles C1 and C2. This is given, my dear friends, with center O and a chord AB in circle C2. This chord AB, as it touches the smaller circle, it happens to be the tangent of the smaller circle. What we have to prove? You have to prove that AC is equal to BC. Prove that AC is equal to BC. Now, what we do construction. We join O with C, join OC, and we observe this is perpendicular. Okay, now proof. Angle C is 90. Why? Because AC is tangent to the circle. AC is tangent to circle C1. OC is the radius of circle C1. That means angle C has to be 90. Now, if you observe in C2, O is the center, AB is the chord. Perpendicular from the center to the chord bisects the chord. This you have done in grade 9. In circles, perpendicular from the center bisects the chord. So we say in circle C2, OC is perpendicular to AB. So it implies that AC is equal to BC. Why? Reason is perpendicular from the center bisects the chord. So AB is chord, it bisects. That means AC is equal to BC. So again, we have applied the tangent radius theorem to this sum. Let's try to move further. So let's try to take a sum based on tangent segment. This will be my question number 3. It says that prove that the angle between the two tangents drawn from an external point to a circle. So there's a circle and there's an external point. So this is my circle. This is my external point. So I'll be drawing two tangents. This is PA, this is PB. So what we are supposed to prove? Prove that the angle between two tangents drawn from an external point to a circle is supplementary to the angle subtended by the line segment joining the points of contact to the center. So you have a center somewhere here. So if I join A with B, this is the line segment joining the 2 points. So this line segment AB, it subtends angle AOB at the center. And this is angle between the two tangents. So we are asked to prove that this angle and this angle, the angle between the tangents and the angle that is subtended by the line segment joining the 2 points of contact, subtending angle at the center, this angle and this angle, they are supplementary. Supplementary means they sum up to 180 degrees. So we need to prove that angle P plus angle O is 180 degrees. Given you could write, this is quite basic. So I'll be simply moving on to the proof part. Prove that angle P plus angle O is 180 degrees. My dear friends, if you observe, this figure is a quadrilateral. PAOB. And if you go further deep, it's basically a kite. Because PA is equal to PB, that we proved. OA equal to OB. It's radii. And angle A is 90, same is for angle B. Why is angle A 90 and angle B? Because angle A is the angle between the tangent and the radius. That's tangent radius theorem. Same goes for angle B. So that means by angle sum property, in figure, PAOB is a quadrilateral. In fact, it's a kite also. Let's take a quadrilateral. It's a quadrilateral. So if it's a quadrilateral, so sum of its four angles is 360 degrees, angle sum property. But angle A plus angle B, both are 90. They are 90. So angle P plus angle B, both are 90. So P plus O, for A I write 90, for B also I write 90, is equal to 360 degrees. So this sums up to 180. So P plus O plus 180 is equal to 360. That means P plus O is 360 minus 180. So that means P plus O is 180. So we have proved that the angles P and O, they are supplementary. They sum up to 180 degrees. Okay. So I would like to give some more information as far as this figure is concerned. Maybe you will use that for different sums. So this was quite basic. So we have applied tangent segment theorem. In the previous two sums, we applied tangent radius theorem. Let's take one more sum where we apply tangent segment theorem. Then we'll move on to the sums where we apply both the theorems. I will be rubbing this. Now, as for this figure is concerned, I just want to tell you something more about this figure. If I join P with O, as lastly we said, these two triangles are congruent. This triangle is congruent to this, we did it. So if these two triangles are congruent, then that means this angle is also equal to this, and this angle is also equal to this, and this is already. So maybe you use it, say x, this is x, this is also x, these two angles are equal. Let's try to move on to another sum, which is based on, see, there are two important sums as far as your textbook is concerned. They are based on tangent segment theorem. Right? I'll be taking both of them. And they are worth 3-mark sums. So question says that if you have a quadrilateral that circumscribes a circle, right? There's a quadrilateral that circumscribes a circle. ABCD is a quadrilateral that circumscribes a circle. You have to prove that the sum of its opposite angles are equal to sum of the other two opposite, sum of the opposite sides are equal to the sum of the other two sides. So this will be our question number 4. So you have a circle, I'm drawing it smaller. You have a quadrilateral. Let me call this as ABCD. This is center. Now this quadrilateral circumscribes the circle. In other terms, we say the circle has been inscribed inside the quadrilateral. You can inscribe a circle inside a quadrilateral or a triangle. Now, what you have to prove? You have to prove that sum of these two opposite sides, AB plus CD, is equal to AD plus BC. Right? Very important sum, worth 3 marks. So given a quad ABCD, so you're supposed to give your best as for any question is asked in the examination. Don't think that, why should I write given? Why should I write to prove? So marks are sometimes being deducted. So do just write give your best as far as any sum is concerned. A quadrilateral ABCD circumscribing a circle. Okay? okay, with center O. So what we have to prove? We have to prove that AB length plus DC length is equal to AD plus BC. And we'll be using the logic that we apply here, we'll be applying that to one more other sum, similar sum. So AB plus DC is equal to AD plus BC. But we forgot one thing. See, my dear friends, the sides of the quadrilateral, they happen to be the tangents of the circle. If you see, these are the points of contact. We should name them. For example, PQ, RS. So we need to mention this. A quadrilateral ABCD circumscribing circle with center O. Let P, Q, R and S be the points of contact. If you want to elaborate it, you could just say in detail that AB meeting circle at PBC and so on. I wrote it in short. So no construction required, we'll simply move on to the proof. So no radius in the figure, simply tangents from external point. So we are going to make use of tangent segment. Now make an observation. See, I have to take AB. So for AB, I will say in figure AP is equal to AS. Because I need AB, so I went to A. AP is equal to AS. Do you know, my dear friends, why they are equal? Because they are tangents from the external point. AP is equal to AS. Same logic goes to PB is equal to BQ. Now you want DC. You want AB plus DC. Move to the other side. See, DR is equal to DS. And CR is equal to CQ. What are all these? In short, they are tangents from external point, or you could say tangent segments. Do write tangents from external points. Because tangents from external points are all equal. So you have four equations. This is equation 1, equation 2, equation 3, equation 4. So what we'll do, we will add them. Why should we add them? Because we want AB. AB is AP plus PB. So when you add at the left hand side, this is AP plus PB plus DR plus CR is equal to BQ plus DS. In fact, AS is in the beginning, okay? AS plus BQ plus DS plus CQ. AP plus PB in the figure is nothing but AB. So write it AB. DR plus CR is your CD, or you could write DC. Both are correct. Now AS plus SD. This AS plus SD or DS, that is your AD. And BQ plus QC is your BC. So we have proved that sum of these two sides of the quadrilateral that circumscribes the circle is equal to sum of the other two sides. So we have applied tangent segment theorem to this sum. And we'll move on to the next sum, my dear friends. The next sum is almost 90% similar to this sum. Now what is in that sum? You have a rhombus. You have a parallelogram that again circumscribes a circle this way, and you have to show that it is a rhombus. In this case, you had a quadrilateral. Now in the next situation, you have a parallelogram that circumscribes a circle. We're asked to show that that parallelogram which circumscribes a circle has to be a rhombus. So we'll apply the same logic there. Up to this level, you have to do the same. Then just one more step extra, and the result is done. So I'll be rubbing this part. So this this is the next sum. I think it's question number 5. I forgot the serial. Okay. Anyway, so you have a parallelogram that circumscribes a circle. Okay. Let me draw a parallelogram. Try to do that. Trying to do the justice to the diagram. Okay, ABCD is a parallelogram. So what are the points of contacts or points of tangency? As we said, PQRS. The center has to be somewhere. Now what should we prove? We are supposed to show that this figure, which is a parallelogram, it has to be a rhombus. Now do recollect in grade 9th. You studied the properties of different quadrilaterals, special parallelograms. We studied there that a parallelogram is a rhombus if its two adjacent sides are equal. A parallelogram is a rhombus if any two adjacent sides are equal. This is already a parallelogram. Now you need to show it's a rhombus. That means I have to show that AP is equal to AD. So given, again worth 3 marks. Important, I should label it. Given a parallelogram ABCD circumscribing a circle, so PQRS they are points of contacts. So what we have to prove? You have to prove ABCD, which is already a parallelogram, you have to show it is a rhombus. So what would you focus on? You will focus on making AB equal to DC, AB equal to AD or AB equal to BC, any two adjacent sides. Now what we did in the previous question, I won't repeat that, we'll make a shortcut. Just in the previous sum, ABCD was a quadrilateral. So by applying tangent segment theorem, you proved that AB plus DC is AD plus BC. So if this question is asked in the examination, use the same logic as we did here. I won't waste time here. I will simply show that, as we proved in the previous, AB plus DC is equal to AD plus BC. So do prove that, as we did in the previous question. AB plus BC is equal to AD plus BC. Now, since ABCD is a parallelogram, so AB is equal to AD because ABCD is a parallelogram. So AB is equal to DC. Opposite sides are equal. Opposite sides are equal. It's a parallelogram. So AB is equal to DC as well as AD is equal to BC. Because ABCD is a parallelogram. So replace this DC by AB. Retain AB. So here AB is equal to AB plus, for DC I will write AB, and AD I will retain as AD, and for BC I will replace by AD. Why we are doing this? We are doing this to make the two adjacent sides equal. And how you got this result? Don't forget, my dear friends. It's not that you wrote it directly. Just now we proved it when ABCD was a quadrilateral circumscribing a circle. So if this question is asked in the examination, you are not supposed to write this result directly. You are expected to give that proof. So to save time, I just applied. Proved in the previous case. Now in this situation, what you have? You have twice AB. And this is twice AD. Dividing both sides by 2, you got AB equal to AD. Two adjacent sides equal. That makes ABCD a rhombus. Understood? So a parallelogram that circumscribes a circle has to be a rhombus. Therefore, you could conclude, therefore, ABCD is a rhombus. ABCD is a rhombus. So, as far the application is concerned, we took questions where you applied tangent radius theorem. Then some of the sums where you applied tangent segment theorem. So there are some questions where you have a mix of both. Means you have to apply both the results. Let me try to get a sum based on that. There are two sums as far as your textbook is concerned. wherein you apply both the results. So I'll be taking, this is one sum and worth 4 marks. Let me take this sum. Right? Okay, I'll be rubbing this. Question is like this: you have a triangle, and there's a circle inscribed. Let me call this as ABC. This is radius 4, this is length 6, this is length 8. So you are asked to find the lengths of the other 2 tangent segments. See, this is point P, this is point Q, this is point R. This length is 6, this length is 8, radius is 4, this has to be 90. We are asked to find the length AB as well as AC. Let's take this situation. So there's a triangle ABC that circumscribes a circle. The radius of the circle is 4, and BR length is 6, CR length is 8. You are asked to find length AB and AC. This is question number 6. Now, if you observe, BR length and BP length are same because they are tangents from external point. So this length is also 6. Same goes to this. CR is equal to CQ. Why? Tangents from external point. So if this is 8, this is also 8. Now AP length is equal to AQ length. Tangents from external point. Let me take AP as, for example, X, and same is for AQ, that is X. So in figure you have BR and BP equal to 6 units because they are tangents from external point. CR and CQ 8, and AP and AQ we suppose they are X. Both of them are X. So to find length AB, AB is 6 plus X, and to find AC, AC is 8 plus X. So how should I find AB as well as AC? We are in need of the variable X. If you find X, put that in AB as well as AC. Now how to find X? Whenever you have to find an unknown, you need to prepare an equation in terms of that unknown. We have been doing this in lower classes from grade 8, in fact. So I need to frame an equation that will involve letter X and solve it. So what we will do? I will join O with B, O with C, and O with A. Now observe, this is one triangle AOB. This is one more triangle AOC, and this is the third triangle BOC. There are 3 triangles in the main triangle. So when you take the areas of these 3 triangles, that sum up to the area of the bigger triangle. So area of the bigger triangle ABC is made up of triangle AOB, AOC, BOC. Area addition theorem or area addition axiom you have done. So if this figure is composed of 3 triangles, take the sum that sums up to the main triangle. So we have to find the length AB, which is 6 plus X, AC, that is 8 plus X. So what I will do, I will be doing the solution. No proof required. This is solving. Given you could write. Now we'll take area of triangle area of triangle ABC. That is made up of area of triangle AOB plus area of triangle AOC plus area of triangle BOC. ABC is AOB plus AOC plus BOC. Now, how do you find the big triangle area? You will have to apply Heron's formula. So let me leave it for the time being. I will move on to AOB. AOB is half a base into height. For all these three triangles, you find their area by half BH. Why, my dear friends? Because this is perpendicular, this is also perpendicular, this is also perpendicular, which is the radius 4, 4 in all the situations. So area would be half a base into height. So for this triangle AOB, it's half a base. Base is 6 plus x into height is 4. Plus for AOC, it's half a base into height. Half a base is 8 plus x into height is 4. Plus BOC, it will be half a base, it's 8 plus x into height is again 4. So for all these three triangles, we are taking the area. Now what I'll do, I will cancel half with this, 2 2 is 4, 2 2 is 4. So this would be 2 times 6 plus x plus 2 times 8 plus x plus 2 times 14. Let me take 2 common. This is 6 plus x plus 8 plus x plus 14. What does that sum up to? I'm not multiplying by 2. This is going to be cancelled to save time. 14 plus 6 is 20 plus 8 is 28. 28 plus 2x. Okay, my dear friends? 14 plus 6, 20 plus 8, 28 plus 2x. Okay? Now, this would be, I could take 2 common. So that is 14 plus x. So my right hand side is 4 times 14 plus x. My right hand side is 4 times 14 plus x. Now we'll move on to the left hand side. This is a little bit bigger. That's why I am taking it in the next step. So left hand side area would be, you have to apply Heron's formula. Just bear with me for 3-4 minutes. We're going to finish this. But do remember the right hand side we got 4 times. I will just save it here. For convenience sake, 4 times 14 plus x is my right hand side. Okay, so we'll rub this part. Now we'll move on to the left hand side, which is to be done using Heron's formula. Right? Now left hand side was area of triangle ABC. You have to apply Heron's formula. Why, my dear friends? Because all three sides are given. There's no other option. It's not equilateral triangle. You apply root 3 by 4 into side square. Heron said area is s into s minus a, s minus b, s minus c, square root of that. What is s? S you need to prepare 6 plus 8 this side plus 6 plus x plus 8 plus x whole upon 2. S is the semi-perimeter. 6 plus 8, 6 plus x, 8 plus x. So 8 plus 8, 16 plus 12, that is 28 plus xx 2x whole upon 2, that is 14 plus x. Yes or no? This is quite obvious. 14 plus x is s. So then area of triangle ABC would be the positive square root. S is 14 plus x into s minus a, 14 plus x minus 14. S minus b, 14 plus x minus b, b is 6 plus x, it would be minus 6 minus x. Into s minus c, 14 plus x minus c. C is 8 minus x, because it's minus times. So 14 goes with 14. X goes with x, x goes with x. So what is left? It's 14 plus x into x into 14 minus 6, that is 8. 14 minus 8, that is 6, but square root of that. So what does this sum up to? This sums up to 48 into 14. No, my dear friends, this is 14 plus x. So 48 into 14. Basically, it's 48x into 14 plus x. This is 14 plus x. We should have written it in brackets. This will give you x. This is giving you simply 8. This is giving you simply x. So 8, 6, 48 into x into 14 plus x. We need to be clear. Now this is my left-hand side. So this was my equation 2. This was my equation 1. What I will do, I will equate them because the area is same. So if we equate them, we are getting an equation in terms of x. So I should write from 1 and 2. 48x times 14 plus x, positive square root, is equal to 4 times 14 plus x. See, 48 will be 16 into 3. So no, right. So can I write 14 as 4 times 3x into 14 plus x? I'm saving my calculations because calculators are not allowed in CBSE. So 48, you wrote 16 into 3. Root of 16 is 4. 3 will be retained inside. So what is the intention? To get rid of this x, dividing both sides by x. Now what should we do? We have to square the both sides to get rid of the square root. So squaring on both sides. So when I square on both sides, I get 3x into 14 plus x. Square on both sides. Root goes. So right side you get 14 plus x whole square. So you have an equation. Is it linear? It has to be linear. Squaring on both sides. So one factor of 14 plus x cancels with this. You got on the left hand side 3x is 14 plus x. So that would be 3x minus x equal to 14. So 2x equal to 14. That gives you x equal to 7. So we have solved this equation. That means my AB length, which is a tangent to this circle, that was 6 plus x. So that is 6 plus 7. That is 13 units or 13 centimeters. And my AC is 8 plus x. That is 8 plus 7. That is 14. Sorry, 15. 8 plus 7 is 15 centimeters. So that has finished. So we have come to the conclusion of this video, and I hope that this is going to extend your knowledge as first